Hi guys, it's Myla here. Welcome back to my channel. So, welcome to the new year, the new semester, or the new academic year. So, today I want to introduce to you guys SWK210, which is the strength of material of the University of Pretoria. So, we're going to be looking at chapter 1. This actually, you know, we're actually going to be looking at like problems. So, you can see we're going to be looking at problem 1.1. So, it says two cylindrical rods AB and BC are welded together at B. The question is determine the magnitude of the force P for which the tensile stress in rod BC is twice the magnitude of the compressive stress in rod BC. So they are basically saying, there's P here, which is unknown. They say calculate the amount of P or the magnitude of P for which the tensile stress in AB is going to be 2 times the compressive stress in BC. Already they are telling us that AB is experiencing a tensile stress and BC is experiencing a compressive stress. Well, because I drew this, it's important to understand that this is actually mounted to a wall. Yeah, it's very much important to understand that, especially because without that, it's going to be really difficult to accomplish that, especially BC experiencing a compressive force or rather a compressive stress. So with that said, now that we know that, now that we have this problem statement, we can simply just start with our first equation. We can say the tensile stress in AB is equals to the compressive stress in BC, and this is going to be our first equation. So because this is what we are told, this must happen. The tensile stress in AB is equals to, 2 times the compressive stress in BC. Now that is the first question. Now moving forward to actually find more information, we can actually look at the tensile stress in AB. So the stress in AB is equals to the force in AB all over the cross-sectional area in AB, right? And we know that the force in AB is P, so it's equals to P, right, all over. The cross-sectional area depends on the diameter of the cylindrical rod, and the diameter is actually 50 millimeters. So we just simply say it's pi over 4 multiplied by 50 squared. So yeah, this is actually the area, and it's important. The reason why we say pi over 4 d squared is because they are saying it's a solid. Sorry, I made an error here. It has to say solid. So it's two solid cylindrical rods. Otherwise, if they weren't solid or they had some form of being hollow, we would have had to use two diameters to find the cross-sectional area. But in this case, because they're solid, we simply use the diameter, which is the outside diameter. So now with that said, if you simplify that, you get, let me just take a long route. You get your P over 1963.50, right? And this is equals to 0.00050929P, right? So this becomes the tensile stress in AB is equals to that. So now this becomes our second equation. So now we have our second equation here, and moving forward we can actually then look at the stress or the compressive stress in BC. So you can just say the compressive stress in BC is equals to the force in BC all over the cross-sectional area in BC. However, there's something interesting here which actually defines your SWK210 or strength of material. Rod AB was only experiencing a tensile, or rather the force P. This is because the two other 120 kilonewton forces were applied here, and because this is mounted to a wall, AB is not really experiencing any influence from these two forces, right? I hope that's clear. Now, well, if it's not clear with time, I guess it's gonna really become much more clearer. However, well, that was AB. However, BC is experiencing three forces. The first two forces, which is the 120 kilonewton forces, they're actually squashing BC to the wall because they are pushed, they are squashing BC to the wall, right? And at the same time, P is actually pulling it away from the wall. This is because AB and BC are welded together at B, as we have been told, right? From the problem statement. And which means if you pull AB, by extension, then, or by default, you pull BC. So which means the force that's acting in BC is actually equals to the two forces, which is 240 times 10 to the power 3, right? Minus P, right? Another thing I need to explain is that I can't really say it's minus because they are in the opposite direction. This is because the two forces are compressive and P is tensile, and that's why there's a minus. But with more problems, I'll keep explaining it, and with many more problems, it's gonna be much more clearer. And I hope we'll actually be able to understand it better. So now, when it comes to the area, we know the area is pi over 4 multiplied by 75 squared. So yeah, this becomes pi over 4 multiplied by 75 squared. This is because the diameter of BC is 75. Now, therefore, BC, or the compressive stress in BC is equals to, when you do the simplification, is equals to 54. I hope it's visible here. It's 54.324887 minus 0.00022635p. This is when you simplify this, you divide this, and you also divide that. So, and that becomes our third equation, right? So now from here, we are done with your SWK 210 element principles. So we are left with the arithmetic. We can simply just do your simultaneous. And to make things easy, we can just simply say substitute equation 1 and 2. Oh, sorry. Not okay. Let me say substitute equation 2 and 3 in equation 1. I hope that's clearer. So what we basically are doing here, remember, initially we said, where's that page here? Remember, initially we said the stress in AB, which is the tensile stress in AB, is equal to 2 times the compressive stress in BC. But now we found the tensile stress in AB in terms of P, which is the one that we want, and we also find the compressive stress of BC in terms of P. So here they are. This is the tensile stress of AB in terms of P, and the compressive stress of BC in terms of P. So what we are doing, we can simply take these two and substitute them in here, and then solve for P. That's why I said by now we are left only with the arithmetic, like your mathematics. And with that said, we can just say it becomes, or let me just say therefore, zero point zero, let me copy, 0.00050929p, right, is equals to 2 times me remove just to make it more mathematically correct. So it's equals to 2 bracket 54.324877 minus 0.000222635p, right? So with that said, if you continue further with simplification, you're gonna get 0.0050929p is equals to 108.65 minus 0.000452722p. So now, and therefore p is equals to 108.65 all over 0.000962026, right? And if you do if you use your calculator, it's gonna give you 112.94 kilonewtons. It's actually gonna give you, let me just try add some additional. It's gonna give you 112.940 newtons, right? And then that is 112.94 kilonewtons. So yeah, that becomes the answer, and yeah, that actually solves this question here that says what is the magnitude of P for which the tensile stress in rod BC is equal to twice the magnitude of the compressive stress in rod. Although this should have been AB, but it wouldn't affect the question. For which the tensile stress in AB is twice the magnitude of the compressive stress in rod BC. So this is the answer. So yeah, thank you guys for your time. I really appreciate you. And yeah, also keep liking and viewing. You can comment, and yeah, look out for some more of the content. I have a desire of also uploading CIR 211, the second year CIR. So I don't have the study guide yet. I tried to check it on the internet, it's not there. But yeah, if anybody actually is willing to help, they can actually comment then, give me some information as to how I can get that. And as soon as I get that, I'll also be uploading the chemical engineering 211 module. So thank you for your time, guys. Stay blessed.